Here are solutions to homework set number 7 for ECE 320 Electronics 1. This homework looks at DC to AC converters, semiconductor relays, and Boolean logic. Now the first problem is a DC to AC converter. This is one version of it, and kind of the idea is I have a transformer with a center tap, tie the center tap to 24 volts. If I take a transistor on the top side and ground it, current flows up. Tie the bottom side transistor to ground, current goes down. So if I chop this, alternate Q2, Q1, Q2, Q1, what the current's going to look like is on the left-hand side, current goes negative, plus, going through the transformer takes you to B2. Now the capacitor adds some filtering so that rather than getting square wave out, I kind of have a resonant circuit right here. What does the waveform look like? Well, if I go into Circuit Lab, like here, let's see. Anyway, here's the circuit in Circuit Lab. Let's shrink this down a little bit so you can see it. Yeah, I'm stuck. Okay, there, it shrunk the screen down. So you can sit there and draw the circuit in Circuit Lab. Oops, I didn't want to do that. And then go under Simulate. I'm going to run it for 80 milliseconds, just skipping the first 40 milliseconds. That's the starting transient. And then make the step size, since the period is 40 milliseconds, 1,000 times smaller, 40 microseconds. If I run that, it'll sit there and do the simulation and show you the voltage at V2. And it takes a while to run, especially when you're running Zoom at the same time. Now when you're done, here's what the waveforms look like. So this is V2, the blue waveform, and I can see the period. The period is 60 Hertz, because my forcing function is 60 Hertz. And here's one cycle. So one cycle starts at 49.5 milliseconds and ends at 66.57 milliseconds. That doesn't really look like a sine wave. So if I use some trial and error, what I can do is play around with this. And I played around a little bit. What I found is 200 microfarads works pretty well. Run it again. I know it needs to go up because the oscillation's trying to happen too soon, so I kind of get that little edge. I want this to have a resonance at 60 Hertz. And, trial and error eventually gets you there. That's not too bad. The blue line almost looks like a sine wave. That's problem 2. Do a Fourier transform on it. So here what I want to do is get the data. So again, one cycle goes from 49.95 milliseconds to 66.71 milliseconds to export CVS file. Open the file, and that'll open up an Excel file that has all your data in it. Pretty neat feature of Circuit Lab. You can take the data, get the data, and then import that into MATLAB. Yeah, pretty cool. Maybe. So here's all your data, and I want to go from 44 to 65 milliseconds. So scrolling down, here's 75 milliseconds. Anyway, take 44 to 65, copy, paste into MATLAB. And actually anything that's 16 milliseconds, one cycle, is going to go from 50 to 66.7 milliseconds. Copy, copy, copy. There's 60, 1, 2, 3, 4, 5, 6, 66.7 milliseconds. Right about there. Copy. I can now go into MATLAB. Say data is start of matrix, paste. End of matrix. Oops. Try it again. Data is start of matrix, paste. End of matrix. And here's your data. This is one cycle. I got the wrong one. Okay, so plotting the correct data. Always good to plot your data to make sure you got the right information. There she is! I got it in MATLAB. Now I can do a Fourier transform on it. So the DC term is the average. It's about 0. The first harmonic. If I look at the period, I'd like the period to be 2 pi, because that makes the math kind of easy. Take the length of data. I have 423 data points. So let's have t go from 1 to 423. Slash 423, that goes 0 to 1, times 2 times pi. So plot t versus data. There it is. My data has a period of 2 pi. Now let's find the Fourier transform. The DC term is the average. The first harmonic is twice the mean of your data hit with e to the minus j omega naught t. And omega naught is 1, because I picked the period to be 1, times t. So there's the first harmonic. Cosine is the real part. Minus sine is the complex part. Second harmonic. That times 2. Notice second harmonic's almost 0. It's almost a pure sine wave. It is not a pure sine wave because I have harmonics. If it was a sine wave, there would be no harmonics. But it's pretty darn close. Third harmonic. Fourth harmonic. And so on. So if you get the data into MATLAB, it's really easy finding the Fourier series. It's just take your data, hit it with the sine and cosine, or if you don't mind complex exponentials, I can get sine and cosine in one shot using e to the minus j omega naught t. In terms of the energy of a sine wave, well, the peak magnitude of the sine wave is the first harmonic. This is the magnitude. The energy is 1/2 of the magnitude squared divided by r. Assuming a 1 ohm resistor, that's how many watts are in the first harmonic. This is how many watts are in the second harmonic. That's how many watts are in the third harmonic. Fourth harmonic, and so on. The efficiency is the energy in the first harmonic divided by the total energy. So I could add all those up, or actually made a mistake here. It should be 1/2 that. 1/2 the magnitude squared. But when I take the ratio, the half will cancel. The net result is this DC to AC converter converts has 99.79% of the energy in the first harmonic. Roughly. I should take this out to infinity. I can do that a second way. Take your data, square it, add it all up, take the average. And I didn't do that right. Anyway, this is the right way to do it. So, back at the ranch. So anyway, using MATLAB, I can sit there and CircuitLab, come up with what the waveform looks like, put the data into MATLAB, find out how much energy is in the first harmonic, and 99.71% of the energy. This graph is the magnitude of each harmonic. So there's the first harmonic, second harmonic, third, fourth, fifth, sixth, seventh, all the way out to 20. So that's, one type of DC to AC converter. Problem 2 looks at a semiconductor relay. So in this case, I've got a full wave rectifier. If I just use diodes right here, what's going to happen is that V1 is going to look like this. It's a full wave rectified sine wave. What the firing angle does is instead, I think this kind of continues on down, this continues on down. Instead of turning on at 0 degrees right here, change color. Let's do this in pink. I'm going to turn on at 50 degrees. So here's 0 degrees, 90 degrees, 180. At 50 I turn on. So it does this, and it's got to stay on until I get to 50 degrees on the next cycle. So this is what the waveform looks like. That's the 4-diode version. There's a 5-diode version that's my preference, but 4-diode is really what's more standard. By varying the firing angle between 0 and 90 degrees, I can change the DC level. Problem 4 is analysis. If the firing angle is 50 degrees, find the voltage of V1 and V2, both DC and AC. Now the DC voltage, here's the equation for it. It's the average of a sine wave shifted by 50 degrees, which is 2 over pi times the peak voltage times cosine of the firing angle minus 1.4. DC voltage at V1 is 6.78 volts. Once I have the DC voltage at V1, I can find the DC voltage at V2. It's just voltage division, 100 over 100 plus 10 times 6.78, 6.16 volts. That's the DC term. AC term. Well, the AC, the peak is right here. There's the minimum. If I approximate that as the peak-to-peak voltage, which is a little bit wrong, but it's kind of what we do in this class, it's a 20-volt sine wave going from 1 to sine of 50 degrees, 35.32 volts peak-to-peak. Take the capacitor at 120 hertz. Again, this is 60 hertz, but it's a full wave rectified sine wave, so this is actually 120 hertz. The capacitor becomes minus J33 ohms. Put these in parallel, 9.9 minus J29 ohms. Inductor becomes J226. Do voltage division. I get 5.63 volts peak to peak. That's what I expect to see at V2. That's problem 4. Problem 5 is be a little more accurate. I know what V1 looks like. It's this blue waveform. Use the Fourier series. Take the DC term, take the first harmonic. The DC term is the same as we did before. I first have to input the waveform into MATLAB, so time just goes 0 to pi in half a cycle. 0 to pi, shifted by 50 degrees. Converted in radians because anything English isn't natural. So V1 is just 20 times the sine of that, minus 1.4, because I've got 2 diodes. The DC level is just like we calculated, 6.78 volts. The AC voltage, however, using the Fourier series, is take your voltage, hit it with the first harmonic. My period is pi, so the first harmonic is at 2 radians per second. If this was 2 pi, it'd be 1. I'm just going 0 to pi, so I got to have a 2 in there. First harmonic is 11.8, minus 11.8 plus J, 7.6. The peak-to-peak voltage is twice the magnitude. So take the magnitude times 2. That's the actual peak-to-peak voltage. Now before we calculated 35 volts, which is a little bit wrong. This is actually the more accurate answer. Using the more accurate answer, I really should only get like 4.49 volts peak-to-peak at V2. Plus there's other harmonics, but those are usually pretty minor. So this is the more accurate answer. A little bit harder to get. If you have MATLAB, it's not too bad. Without MATLAB, I would not want to do this. But that's the beauty of MATLAB. If I can get the waveform into MATLAB, I can find the Fourier coefficients. All I really care about is the DC term and the first harmonic, and that's what the orange waveform looks like. This is the DC term of the blue line, and the first harmonic. That's the AC term. Problem 6 is more of a design. Design a circuit that outputs 9 volts DC with 1 volt peak-to-peak ripple. So to get the DC term, I know that if V2 is 9 volts DC, V1's got to be 9.9 volts DC. Throw it in the formula, my firing angle should be 27.43 degrees. Using the slightly incorrect formula, that's easy, that says the peak-to-peak voltage at V1 should be 29.2 volts peak-to-peak. It would be more accurate to use a Fourier series, in which case it's actually 21.7 volts peak-to-peak. Either one's fine on the homework. Again, this one's more work. It's going to be a little more accurate, though. I forget to do something? Oh, yep. Then you got to find C. To find C, so now that we know V1 peak to peak, I can find C2. Assuming C2 is 0, I can calculate the ripple at V2. It's going to be 8.63 volts peak to peak, roughly. I want the ripple to be 8.63 times smaller, so pick C2 to be 8.63 times smaller than 100 ohms. So we want it to be 11.58 ohms at 120 hertz. Solving for C2 is 114 microfarads. Problem 7 looks at Boolean logic. Implement the following logic using NAND gates. And what that means is circle the ones. So here's one way to do it. I get the blue line, which is A bar, D bar. The green, which is A, D. And the orange circle, A, B, C bar. I can implement that using AND gates, so it's A bar and D bar, ORed with A and D, ORed with A, B, C bar. Then throw in double negatives to turn the ANDs into NANDs, to turn the OR into an AND also. So that's using NAND gates, circle the ones. To use NOR gates, you circle the zeros. So here's one group of zeros, second group of zeros, third group. Since it's circle the zeros, this is Y bar. That'll be the blue circle, which is A bar D. The green circle, A, C, D bar. And the orange circle, A, B bar, D bar. Now you use De Morgan's law, negate both sides. Not Y gives you Y. AND goes to OR goes to and flip the sign of everything. So A goes to A bar, D goes to D bar. I can then implement that using OR gates. So that's A or D bar, ANDed with A bar or C bar or D, ORed or ANDed with A bar, B, D, OR together. Throw in double negatives, that turns OR into NOR, and into NOR also. So that's kind of how to use NAND gates and NOR gates. NAND gates, you circle the ones. NOR gates, you circle the zeros. And that is homework set number 7 for ECE 320.